gamma rays and cosmic rays and shock waves. What's your best way to create high-energy phenomenon?
Once we had the Large Hadron Collider going, from the rates of bajillions of collisions that they're doing there, we were able to figure out basically the interaction rate of protons at those high energies.
So you have muons in your exotic places in the universe, but I hear that we also detect muons here on Earth.
The Earth's atmosphere is a bright, bright gamma ray background. So that particle shower, these extensive air showers, they'll come flying in and those muons will stream down to the surface. 1,000 just went through your body.
You gotta love science, people. You just gotta love it.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. We've got a cosmic queries lined up for you. And that means I got Chuck Nice in the house.
That's right. What's up, Neil?
All right, good.
Feeling good.
Good. You know, I'm mining my colleagues once again.
Sounds illegal.
Tim Paglione. Tim, how you doing, man?
All right.
Welcome to StarTalk, your first time.
Thanks, yeah.
Have we known each other how long?
Probably like 20 years.
Man, welcome
Thank
to
you.
the show. You're a fellow astrophysicist. You're a professor at the City University of New York.
Nice.
At the Graduate College.
Excellent.
And at York
Yep.
College, one of the campuses of the CUNY system. And we have Astrocom here. And what is Astrocom short for?
So full name's Astrocom NYC, and the com in Astrocom is community. So it's all about building community.
Okay, and you'd mentor students within that community.
Yep, it's been 74.
74 students?
Yeah, we've been going for
Wow.
a dozen years now.
Yeah, because it's not good enough just to be a scientist if you just, you know, live on an island.
Right.
You got to pass the torch at some point.
Well, let's
Share the
hope.
torch.
Yeah. That's a good island
Yes.
where scientists are actually bringing up other scientists.
Right. They don't vote you off the
Yeah,
island.
they don't vote you off the island.
They bring you into the island.
Yeah. Unless you say you believe in astrology. Then they're like, you got to get out.
No, a good educator will then show them why that's in error.
But let's be honest. Let's just be honest here.
then you vote them up.
So one of the reasons why we have you here is you've done a lot of thinking and a lot of observing and a lot of publishing about extreme objects in the universe. And people love them some extreme things.
Everybody
Yeah.
loves extremes.
We love it.
So you go big or you go home.
Yes.
Yeah, super fun. That's the stuff.
Yeah.
Nice.
So as we ascend the electromagnetic spectrum in energy, and we go red, orange, yellow, green, blue, violet. I left that.
You skipped it.
I skipped indigo because indigo doesn't belong there. That's Isaac Newton being mystically fascinated by
You
the
broke up Belle Biv DeVoe.
I don't think
Roy
that was
G.
his
Biv,
name.
not Bell Biv. Roy G. Biv. Right. So violet and then ultraviolet, which can give you skin cancer. And then X-rays, which will give you
Bone cancer.
organ cancer, and now gamma rays.
Yeah.
That turn you into the Hulk. So
They go right through you.
So tell me about what makes gamma rays in the universe. Because we know stars make regular light, and we also know black holes in their vicinity, they can heat up the gases and they'll radiate ultraviolet and X-rays. But gamma rays seem to just come from their own places.
Yeah, it's the most energetic light that there is, so you need a really super energetic process. So you have to blow something up or have a huge shock run through an area to accelerate particles to nearly the speed of light.
Shock means something very specific in astrophysics. So tell us about that. Because otherwise, shock, what does shock mean anywhere?
Oh, dear.
That's not what we mean.
Did you see what that black hole did? Dude.
You were shocked by the shock. Yes.
So, I mean, simply put, in a certain area, there's a speed of sound. And if you go beyond that, that's a shock.
You make a shock.
Make a shot. Right.
Yeah.
Right.
Just go beyond it. Like, so you need a process that will overtake something as fast as the speed of sound in that medium.
That's right. So like an explosion, if a star explodes as a supernova, it'll send a shock wave out through the interstellar medium, and that'll bunch up all the gas into high density. It'll bunch up all the magnetic field.
So let me ask you this.
Yeah.
When you look at...
Wasn't he in the middle of explaining something?
No, it's
No,
cool.
that was... okay. So in the medium itself, all right, air is the medium through which the shock wave of sound travels, right?
sound that
right.
we're doing right now.
Here on Earth.
Here on Earth. So in space, if it's a vacuum, what exactly is the shock traveling on?
Good question.
Yeah. There's always a little bit of something going on out there.
Oh.
Yeah. And so anytime there's any kind of discontinuity, we would also describe as a shock. And the things that I'm most interested that'll create gamma rays, these high energy particles called cosmic rays, they're accelerated by these bunched up, shocked up magnetic fields.
Okay. There you go.
Shocked up. That's a state.
That is a made up phrase.
Shocked up. Just like you jacked, I'm shocked.
Yeah, I'm shocked up, baby.
Exactly.
Tell you right now.
All right, so in that one sentence, you mentioned gamma rays and cosmic rays and shock waves.
Yeah.
Right, all of this. And this is high energy phenomenon is where you're coming from here. So what's your best way to create high energy phenomenon? I know we can do it in the accelerators.
Yeah.
Right?
Yeah.
So does our understanding of the accelerator help us in your job?
Actually, it really does. So once we had the Large Hadron Collider going
in Switzerland, the CERN.
CERN.
Yeah.
So from the rates of, the bajillions of collisions that they're doing there, we were able to figure out basically the interaction rate of protons at those high energies, and that made actually my models of those proton-proton collisions in the interstellar medium a little more accurate, which was kind of nice. But we work at way higher energies.
Than you mean the universe?
The universe. Yeah.
He's taking credit for the universe.
That is the super mega royal
my people,
we.
my stars, it's the royal we if there ever was one.
Exactly.
And so you're accelerating protons to much higher energies than even the most powerful accelerators on Earth.
Yeah, that's right.
Okay. And now they're fast moving. Can a single proton make a shock wave? No, right? What goes on there?
No.
You need a wave of them. I mean, a bunch of them.
Yeah, you need a bunch of them. But as long as they find another proton out there, like an ambient proton, which is just a hydrogen atom.
Ambient proton.
Right.
Yeah, these are the sleepy ones. The one's not looking.
Yeah.
Ambient.
Ambient. Okay, go on.
So if there's just an interstellar cloud out there, it's just hydrogen minding its own business.
Just hanging out.
Gets whacked by one of these high energy protons, that'll create a bunch of other particles. It's a nuclear reaction. And just like you get at the particle accelerators, and all these things come out, these pions come out. Some are positively charged, some are negative.
So they call all those daughter products.
Sure.
But never son products. I was wondering.
Daughters very rarely disappoint. Sons often do.
I wonder if it was Marie Curie that did that.
Oh, that makes sense.
Good one. Interesting.
So cool if it was.
Yeah.
It would be.
Yeah.
And it's dateable to that point in time, right?
Oh, for sure.
Because that's when we see the
first person to
byproducts.
see the X-rays. Yeah.
That's where the alpha, beta, and gamma rays were first named.
Yeah.
When we didn't know what they were. That's just the first three letters of the Greek alphabet.
Makes sense.
Yeah.
So they were just some source of energy moving out of your experiment into somewhere else. So an alpha rays became what? What did we discover those to be?
Those are helium nuclei.
Yeah, that's kind of weird, but all
Yeah.
right. The nucleus of a helium atom, alpha rays, okay?
Yeah.
We just call them rays because we didn't know, because we couldn't distinguish the energy of a wave from the energy of a particle.
Wow.
Those idiots.
Yeah.
Okay, alpha. Beta,
Turned out to be electrons.
just electrons.
Just electrons.
We go from the helium nucleus
Right.
to an
To an
electron.
electron.
See, that ain't right.
That's right.
And
That's
alpha, beta.
wild.
They had a really interesting result, though, because they had a whole bunch of different energies of electrons, of beta rays, would come out. And that led Enrico Fermi to say, there must be something else carrying this extra energy. And that turned out to be some little tiny massless particle with no charge, which is a neutrino. Neutrino.
Neutrino.
It was little.
Right.
So
Yes.
it was a little one.
Which, yeah.
The Eno.
The Eno makes
Yeah,
it
it makes
little.
it little. And neutral is neutral.
Right.
Yeah.
Right.
So the energy budget was not resolved.
That's right.
That's in the.
There was always some leftover.
So,
Yeah.
okay. So is that the residual, the neutrino itself?
Yeah.
Okay.
Yes,
Yeah.
that's a
That's
gangster
really,
prediction.
That's badass.
Right. If you say
Yeah.
we're missing energy, therefore there's a particle with no charge that carried it away that we didn't detect.
That's
That's making
that's
shit up.
Totally.
just to fill in the blank.
Yeah.
yeah, and it turned out to be exactly the case.
Oh,
That's
yeah,
so
for sure.
Wild. Mm-hmm. Wow, that's
Yeah.
very cool, man.
It is.
All right. So now tell me, the proton hits what to then make a shower of other particles? Another proton?
Another proton, yeah.
Okay. And so it busted open the proton.
Mm-hmm.
And when my classical knowledge of nuclear physics ends with the quarks that are inside.
Yeah.
But I guess you can pair up quarks and make particles that are not protons but are lighter than protons?
Yeah. So, well, pair them up. Yes.
I guess.
Yeah,
I don't know.
Yeah. So, I mean, from this reaction, from the proton-proton interaction, you end up, primarily you get muons. Oh, well, you'll get some pions. Primarily pions are the ones that interest me the most. There's positive ones, negative ones, and neutral ones. The neutral ones with no charge, they immediately decay into 2 gamma rays, which is usually what we see.
So there's a whole chart of what's going on there that you need to be fluent in. Otherwise, you don't know what the hell's going on.
Yeah, kind of.
Okay, remind us about muons, because I'm fascinated that they exist at all.
Yeah, because they're very short-lived. And so this is one of these interesting...
Can you quantify that short-lived?
Can I quantify that?
I mean, short-lived, a few seconds, a few microseconds.
Way smaller, way faster.
Even
now.
shorter than that?
Yeah,
Okay.
yeah.
Right.
In fact, the time it takes a muon to reach the surface of the Earth from space, from the atmosphere, where they're created by these cosmic rays hitting the atmosphere, they shouldn't live to get to the surface. Traveling at almost the speed of light, they shouldn't make it, and yet they do. And this was
They
one
should have decayed before
Yeah,
they
I was
Yeah.
going to say they're okay.
Yeah. But the trick is that they're traveling so fast that their clock's at a different speed than ours.
Oh, that's amazing.
Ain't that some stuff? So you have muons in your exotic places in the universe. But I hear that we also detect muons here on Earth.
Oh, yeah.
So what's going on there?
So you'll get one of these energetic cosmic rays will come in and hit something in our
So
atmosphere.
it's the same phenomenon.
Exactly the same.
Right.
Yep.
But
in
that's
fact,
happening to us.
the Earth's atmosphere is a bright gamma ray background, in fact. So that particle shower, these extensive air showers,
Because it busted open the proton.
Right.
Okay.
they'll come flying in, and those muons will stream down to the surface. 1,000 just went through your body.
Wow.
Another 1,000.
Another 1,000.
But the interesting thing is their lifetime is so short that they shouldn't make it. That trip from the top of the atmosphere down to here, they should decay
They should
before
decay
that.
before they hit
Long before they hit the
before
Earth.
they hit the
Yeah.
Earth. Then why do they make it?
Well, because they're traveling so fast that their clock is running at a different speed than ours.
That's amazing. So they actually don't know any better.
So Einstein was right.
It's
So it's relative time dilation.
time,
Yeah.
time dilation
Yeah.
right here on Earth. It's you gotta love science, people. You just gotta love it.
Yeah, can't argue
He
with
blows
that.
a gasket every now and then. You got to let him.
that's
you
just-
got to recover from that.
So phenomenal.
And muons, they behave like electrons, right?
Yeah, except there
But
could
why
be
aren't they
positive
electrons?
ones too. Well, they're different.
Thank you, Professor Paglione.
They're fundamentally different. I mean, they've got mass. They're not a fundamental particle like an electron, things like that. Yeah.
But they're analogous to an electron, and why?
Yeah. Well, there are muons with negative charges. Electrons have negative charges.
Right.
But if you leave a muon alone, it'll decay, and you can get an electron from that. So in a way, you could think that an electron's kind of hiding inside a muon.
Okay. That's weird.
Yeah.
Okay. All right. So these energetic phenomena, I think, because we're colleagues and I hear, the most energetic things I know of are supernovae, and then there's hypernovae.
Okay.
What are those things, hypernovae?
That would just be a big ass explosion. I don't really know. I mean, there are supernova that are just extremely energetic. They're hard to explain. It's the
Badass supernova.
Yeah, you're right near the edge there.
Is there a quantifiable magnitude of nova, supernova, hypernova, like that we would be able to understand as a regular person? Like,
You're not a regular person. Let's get that straight.
yeah, you know what I mean? Like,
We have a hierarchy of words,
yeah.
and how do they correspond to hierarchies of energy? Is that what you're trying to say?
That's what I'm trying to say. Like, how would you explain, like, okay, so a nova is like 10 nuclear bombs or 5 hydrogen bombs or whatever, just so that we could, like,
I wish I had that number, but I think it's more of those bombs than I could put that
more
number
than we
to.
could ever even
Yeah,
imagine.
it's
more
a
bombs
lot.
you can imagine.
Yeah.
That is dope.
I mean, you get 10 to the 53 ergs from what we call a type 2 supernova explosion. So that's a massive star that'll explode and end up as a black hole.
Right.
And that's like a factor of 10 to the 20 more than a nova, just a little.
10 to the 20 more.
Yeah, it's a huge difference.
Yeah, in fact, in that explosion, correct me if I'm wrong, it's emitting more energy than all the stars in the galaxy in which it explodes.
Yeah, that's something. I mean,
think that's right. If the sun is 10 to the
comparable,
33
yeah.
ergs per
Yeah.
second, and it's 10 to the 53 total ergs,
yeah.
So that's 10 to the 20th more ergs.
The one that I've heard is if you add up all the energy that the sun will ever emit in its total lifetime, that's like a supernova.
That's a supernova.
Yeah.
Gotcha.
Right.
It's huge.
Yeah, that's almost the same way to
So
think about the same problem.
all at once.
All at once.
You're looking at 10 billion, 15 billion years
Yeah.
of radiation all at once.
Yep.
And that's why, so they're visible across the universe. So how far away are your objects? Are they all in our own galaxy?
Everything that I've been studying lately has been in our own galaxy, but I've also studied other galaxies, but nearby ones mostly.
Okay.
But now I've just started getting into galaxy clusters, but still nearby clusters.
Okay.
But they're getting kind of far away now.
Let's just take a moment as we record this in the year 2024.
Yes.
That 100 years ago,
Yes.
Hubble, the man, not the telescope, discovered that we're not alone as a galaxy in the universe.
Wow.
Yeah.
Ended the great debate.
No, he didn't do the debate.
No, he ended it.
Ended it.
He ended the great debate.
Okay, the great debate was, are the spiral nebulae just local phenomena in our own galaxy?
Right.
Or are they whole other galaxies out there like ours?
Yeah.
Island universes.
And now we know there's a whole trillion of them out there.
Yeah.
Yeah.
That's
They
amazing.
got out of control.
Look at that.
So you mentioned Enrico Fermi just a moment ago as the
neutrinos.
Was he the namer of the neutrino? He must
believe
have, 'cause he
so.
was Italian.
Yeah.
Neutrino.
Makes sense, yeah. That's exactly how he said it, too. I believe I have a discovery. It's got a neutrino.
Exactly. That's Chuck speaking Italian. As
There you
far as
go.
By the way, that's every American who's not Italian speaking Italian.
And if there were girl neutrinos, they'd be neutrinas. Right? Wouldn't they?
That's very cool.
Yeah.
Now I'm interested.
So we tend to name telescopes after scientists or other people relevant to our field. And I read recently about the Fermi telescope, and I don't know anything about it. Could you catch me up on it?
Yeah, so it's a gamma ray. It's the Fermi Gamma Ray Space Telescope.
Wow.
A space telescope.
Yeah. You got to be in space because gamma rays will interact with the Earth's atmosphere. So
And give you muons.
yeah, and pions and the whole gamut.
Yeah.
Good stuff. So it's in space.
Is this the first gamma ray telescope, space telescope?
It is not. So its predecessor was the Compton
Oh,
Gamma Ray
I knew that.
Observatory.
I knew that. Okay.
It's the size of a bus. It was a really big one.
Because it's a bus that fits inside the space shuttle.
Yeah.
So
Just.
yeah.
Yeah.
So
Yeah.
it's not that it just fit in. It's designed to just fit in.
Oh, for sure.
That's your size. Just fit,
Right.
make it fit.
Yeah, that's your whole payload.
That's the whole
Right here,
payload.
like
yeah.
right there. Yeah.
At the time, and it may still hold the record, it was the heaviest thing that the shuttle ever launched.
Really?
Yeah.
Wow.
Okay.
But you need a heavy detector like that to stop the gamma rays, to detect them.
Gotcha.
It's in essence, the Fermi Gamma Ray Space Telescope is a particle detector.
Okay.
But it could also know what direction it's coming from. Right?
That's right.
Yeah.
So it detects when a photon comes in, and it's one photon at a
Gamma
time.
ray photon.
Right.
So when the photon comes in, where it came from, as best as it can,
You're counting one photon at a time?
one at a time.
That's insane.
They're
What?
rare. This is the highest energy stuff. You need
Gotcha.
something special to create it, and
Right.
so they're pretty rare.
Man, they're just
Dishing them out.
here. Here's one for you. Man.
One for you, one for you.
And one
We
over
got
here.
a photon, guys.
And
guys.
they're looking over here. Let me toss one to those
we got another one over
aliens.
That's pretty wild, man.
I mean, when you
Yeah.
talk to solar astronomers,
Oh gosh.
you can't even have a conversation.
Yeah.
Because they have like countless photons coming from the sun.
Even us, just from anything, from a star, you get countless photons.
Yeah.
So they're precious, one photon at a time.
Okay.
So what will it do that the Compton Observatory couldn't do?
Fermi was a great improvement on that localization, like figuring out what the direction was. So it could pinpoint the direction of the gamma ray much better. That was really important.
Because I think there's whole generations of detectors where they just detect something
Right.
and there's no information as to where it came from. It just detected
Just
it,
right.
right?
And it was even worse with Compton because you would really like to say, oh, we detected a gamma ray from this crazy source. But you couldn't quite pinpoint, did it really come from that crazy source or not?
Your uncertainty circle was huge.
Exactly.
Yeah, okay. So now you're doing a little better.
Oh, a lot better. Yeah.
Okay.
To, a fraction of a degree. It still sounds pretty sloppy.
So, observer that you are, space telescopes have high value to you, being above the atmosphere,
Oh, yeah.
detecting your one particle a year or whatever. Your one photon.
Luckily, it's more than that.
Okay, I'm happy to hear. All right, how many total gamma ray photons have you touched in your life?
Oh, that's been plenty.
Plenty? Okay.
Yeah. Like I was saying before, any time one of those cosmic ray protons hits an ambient proton and the galaxy is full of those gas clouds, they light up.
Oh, God. Okay.
Yeah, so actually it's a strong background.
It's a strong background.
Yeah.
Okay. All right. So you use the Fermi telescope.
Mm-hmm.
In what way?
I've lately been studying, things that you can't detect, oddly enough. So there's all these different gamma ray.
You're detecting it with gamma rays. I mean, you think you can't detect with a regular telescope?
No, you can. There are bright sources of gamma rays like pulsars and star-forming galaxies and things like that. But, if you look at all the pulsars that are out there, there's about 5,000 or so that have been detected in the radio. And many of them are detected as gamma ray sources as well, but only a couple of hundred, about 300. So what are the other 4,000 or so doing? We suspected that they would also be good sources of gamma rays. And so we were looking at all the gamma rays.
Just a weaker source.
Yeah.
Okay.
So we were looking at all the undetected pulsars and gamma rays and stacking that signal together to see if, as a population, they actually are gamma ray sources, and trying to figure out what their
So when you
properties as a
stack,
population
you are
are.
improving the signal to noise of your data.
Yeah, exactly. It's the signal compared to the noise. We're trying to reduce the background.
So every time you stack, the noise slowly cancels itself because it's not additive, right? The ups and the downs cancel.
Ideally.
You have a signal, however low, if it's really there, every next time you're going to boost it.
It's amplified.
It's amplified, and every next time you're going to tamp down the noise.
Yep.
Right.
In real practice, with a particle detector like this, the background just always adds up too.
It does. Oh, man.
But you do get a persistent additional signal from your source population. So we stack them both.
You have to beat it. You have to beat it.
Yeah, we stack them both.
Okay.
Stack the background, compare it to our targets, and then we get a signal above the background. Yeah.
Okay. And so in the inventory of objects or phenomena that are in these catalogs that emerge from the stacked data, is it something other than a pulsar or a supernova? Or are you discovering new kinds of objects?
Maybe, because pulsars at very low gamma ray luminosities, some people say they shouldn't do that. And we're discovering that we're seeing them, that these low spin down, they're called low spin down pulsars, are actually potential sources of gamma ray emission. So there's just a lot that we don't know about the gamma ray production of pulsars. It comes out in a wacky area of their magnetosphere. And
So does it feel good when someone says...
Can you just for the sake of the people who may not know, because I know.
For others.
For the other people. Like, what is a pulsar, and why is it so important when you talk about spin?
Yeah, so a pulsar is the densest kind of object in the universe that we can measure. It's all the superlatives like that, right? It is the densest. We're talking something a couple of times the mass of the sun, but the size of Queens.
Okay.
So super compact.
That's wild.
Can't go any more compact or you get a black hole.
Queens, a borough of New York City.
So it's
for international...
It's a black hole that you can actually observe. Or right before a black hole that you can actually observe.
Exactly. Yeah. So super dense. Because of that, it has an incredibly high surface gravity, right? So like 100 trillion times the surface gravity that's keeping us in our seats right now.
Oh.
So if you weighed a pound
Right
here, you'd weigh 100 trillion pounds on the surface of a neutron star.
You'd be flat as a flapjack.
Exactly, right. You'd be a grease spot.
Spot, that's all.
It'd be a
Not
spot.
even flapjack.
Right, just a spot.
Not even a tortilla.
Right. A little spot.
But then they pulse, right?
Right.
This pulsing is that they're spinning around really super crazy fast. Also, some of the fastest spinning things. They spin faster than a blender.
Okay.
Double the mass of the sun, the
Right.
size of Queens.
Size of Queens.
Spinning
faster
faster.
than a blender.
Yeah,
Wow.
yeah. It's pretty nuts.
That's wild.
Spinning so fast they could almost fly to pieces. I mean, it's that fast. Because of that fast spin and that high compression, they have these powerful magnetic fields, like trillion times higher than the magnet that's on your fridge. And that generates these intense electrical fields that'll accelerate particles, just like the particles at the particle accelerators
That's
here
your
on Earth.
particle
That's your
accelerator.
particle. Yeah.
The universe as a particle accelerator.
Look at that.
And even though the surface gravity is so high, any particles that are near the surface, and these are just electrons and stuff like that, they will be, instead of falling to the surface, despite that high gravity, they get shot off at almost the speed of light because of the intense electromagnetic fields.
Look at that.
So that means we understand gamma ray bursts. Is that what you're saying?
That's a stretch,
Okay,
but
okay.
yeah.
All right.
So a gamma ray burst is a different thing. So this is during a stellar explosion, like a supernova. Something happens as the core of that star collapses, and
Anytime
then
a scientist says something happens,
yeah,
Right.
we're gapping ignorant. There's a whole ignorant valley there.
Right. There's a whole world inside
A
of
whole
something
world,
happens.
right?
Well, people are modeling it and getting pretty good at it. There's a student in our group, a master's student, who's been doing these gamma ray burst explosions. But
Master's degree,
yeah,
not just a master
Of the universe.
or master class,
Which
or
would be kind of cool, though,
a
if you're
master's
an
degree
astrophysicist.
student. Yes.
Yes.
Okay.
That'd be the degree they should give you as an astrophysicist. You are now a master of the universe.
that I'm in favor of.
Yeah,
That's
we
pretty
should change
awesome.
that for sure. Well, let's look at our cosmic queries and see what came in. Chuck, you have them all?
I have them right
You got them all.
here.
All right, bring it on.
Yeah. Well, let's start with Haywood from Atlanta, Georgia says,
Haywood's asked before. I think Haywood.
yeah, he says, hello, Neil, Tim, Chuck. Just wondering, do gamma ray bursts start slowly and build over time, or are they instantaneous? And by that, I think he means not the actual explosion, but the lead up
Is it
to.
fat?
Because there's no such thing as a slow-moving burst.
Right. You wouldn't call it a burst.
You wouldn't call it a burst at that point. So leading up to the actual, expulsion of what we just talked about, what's that process? Do we have an idea of what that process is?
Yeah, so it's the collapse of a massive star down to a black hole, presumably. But then instead of just like this spherical explosion that you might picture, it's actually you get a couple of jets of explosive material, basically that blast out of the star, and those jets tend to be pointed right at us, and that gives you a lot of that high energy emission once it breaks out of the star.
Right.
But it's seconds. It's a really rapid rise, and then there's a slight fade, but it's still seconds, maybe tens of seconds, and those are so-called long gamma ray bursts. There are shorter ones that are much, much quicker.
Tens of seconds, and that's the long
Wait. So
Yeah.
how do you know it's that short? Has anyone witnessed that?
Yeah, we see the light curves of their explosion, and then the
So somebody's
the quick
looking
fade.
at it before it explodes,
Yeah.
and then they see it while it's exploding in those tens of seconds. Even though the sky is vast, and with not enough astronomers in the world to look at every star at all times, but you had people looking at the right star at the right time.
Well, not just people. The Fermi Gamma Ray Space Telescope has an instrument that's looking at the whole sky all the time.
Oh, there you go. Okay, so it wasn't a pointed observations. It was a broad
It's part of a survey.
survey.
Yeah,
Okay.
exactly.
All right. Give me more, Chuck.
Let's keep moving. Let's go with Warma, or is it Rama, who says, hello, Dr. Tyson, Professor Paglione, and Lord Nice. Andrew here from Cork in Ireland. And then he says, I suppose it's in Gaelic, 1,000 welcome, 100,000 welcomes. And I'm not going to try to pronounce that. Sorry, buddy. He goes, my question for you today is, can you explain how the properties of the largest molecular clouds in galaxies influence star formation rates and the overall dynamics of galaxies?
I love
Okay,
that.
that's a great question.
Yeah.
That's a really great question.
Yeah, this is where I started before doing the gamma rays. Was studying these star formation and giant molecular
Was your
clouds.
PhD on that?
Yeah.
Oh, cool.
Oh, cool.
Yeah, in fact, there's not a word of gamma rays went into my PhD thesis, but the one paper I did as a grad student on it was one of my most highly cited papers.
Nice.
It's kind of funny. And now all I do
downhill
is
since
gamma
then.
rays.
Yeah.
I was waiting for Fermi to get launched. Yeah, the star formation happens in these giant molecular clouds. And so that's where all the action is. So yeah, the properties of the molecular clouds definitely determines how it all plays out.
Wow. And do the any of these other phenomena, like, I don't know, the collision of black holes or these pulsar ejections and all of these particles that are excited and then jetted across the universe, do they ever perturb these other, like clouds and things to cause something that we can observe? Or
It's interesting when you're talking about black holes and this and that. I'm rolling in my head. I'm like, no. But the cosmic rays that we've been talking about, they can penetrate into the molecular clouds deeper than anything else,
Okay.
and provide a source of heat. And what we've noticed is that molecular clouds are a little hotter than one might predict. They should be really cool.
They're absorbing their...
And so there seems to have always been an additional source of ionization, source of heating, and cosmic rays are that source.
Okay.
And this is one of the things that keeps me going in cosmic ray astrophysics is seeing what the contribution of cosmic rays are to galaxy evolution and molecular cloud evolution, star formation.
So molecular clouds can be huge. That means they have a lot of gravity. Mm-hmm. Is that enough gravity to influence other clouds? Or are they just into its own thing?
Interesting.
I mean, they can merge and do other stuff, but they tend to be really, subject to the overall dynamics of the galaxy. So they'll follow the gravitational potential of the galaxy.
All right, this is Ilya. Ilya says, hello, Dr. Tyson, Professor Paglione, and anyone else who might be there. Thanks.
Your title is Lord.
This is true, yes. Here's a question from beautiful Portland, Oregon, from the limited knowledge. Gamma is the highest photon energy we have encountered in the universe, but we have also produced photons with much higher levels in particle accelerators here on Earth.
Nope.
Does the equipment you use in your studies have the capacity to detect and differentiate such particles? But the truth is, have we really?
No, you can't compete with the cosmos, man.
Right?
No, they totally have us beat.
So the cosmos is a they in that sense. I'm just...
Sure.
How you're personifying the universe.
The LHC is able to bang together protons at, I think it's like 14 tera electron volts, which is just a whole crap load of electron volts. It's very high energy. But we've got their sources out there that work 1,000 times higher.
1,000 times higher.
We're getting cosmic rays and there are gamma rays that we're seeing from sources that we truly don't understand how they can be that energetic.
Isn't that our best evidence that the Large Hadron Collider would not create mini black holes that would eat Earth when they turned on the switch?
Oh, that's an interesting question.
Yeah, because the energetics of the collider, though high, pale compared to the actual collisions happening in our actual atmosphere.
Yeah.
And so you can't worry that that's going to turn us into a black hole when the
you have
universe,
higher energy reactions that are happening right above us all the time.
All the time.
Yeah.
That makes sense.
Yeah. I think the record is 20 TeV for the highest energy photon detected on the Earth. It might be higher now, but that requires a process or a particle that's even more energetic. And so they're out there. They're out there, and we can't touch that.
Can't touch it.
Can't touch this.
So this is Kayla Badu. She says, salutations from Lafayette, Louisiana. Kyla here, curious about gamma ray telescopes. How exactly do they work? Are they used to investigate, and why do we never hear about them?
I know. How come? Because you don't make pretty pictures.
I don't know.
It's got to be it. People like pictures.
Yeah, that's
You
true.
say, I had 3 photons today. That does not make a headline.
Oh.
Yeah, the pictures are kind of grainy. I'll admit that, but we usually
That's why there's Photoshop.
or artist's impression. Yeah. It's a particle detector.
Right.
So the particle comes in, it goes through these layers of tungsten, basically, and it'll create a particle-antiparticle pair, and that pair travels through the tracker, the so-called tracker, and that lets us know where it came from. Oh. And then it lands in this silicon calorimeter, which is just an energy measurer. And that's the way it works.
All right. So that's super cool, man.
So what, tell us about a calorimeter.
So the particle eventually ends up in this calorimeter, and that's just overall measuring the total energy.
Okay.
Gotcha. Like a collection
plate. So, we like I said, we get three things.
Its root is calorie. Right?
Yeah.
Yeah, calorie is energy. Yeah,
Energy.
calorimeter.
Oh, cool.
Yeah.
Calorie. So it's heat.
Yeah.
Okay.
Or energy.
Energy. Right. Yeah, exactly.
Which can manifest.
It can
as heat.
manifest heat, but it's
That's right.
energy. Excellent.
Technically, heat is exchanged energy.
Gotcha.
Yeah.
Cool. All right. You see how specific these scientists are, people? You see what a pain in the ass this is?
But it facilitates efficient communication.
That I cannot disagree with.
That's what I'm saying.
Right. All right, here we go. This is Christopher Stowe, who says, hi, Chris in Pennsylvania here. My question is about the chemistry that occurs in these huge clouds. Is there complex chemistry occurring in the nebula, or is the material too diffused for this to happen? This
Good
guy knows
question.
what he's talking
Yeah,
about.
that's really insightful because
Freaking dude knows what he's talking about here.
it is diffuse, extremely diffuse. You might, in a dense molecular cloud, you might have 1,000 particles in a cubic centimeter, so the size of a die. You know, so that's not much. So they don't interact a lot.
A die, you mean a dice?
One die. Yeah,
One
yeah,
dice, right?
So yeah, the chemistry's there, but it's slow. Gas phase chemistry is just really slow.
Slow because of the separation among the frequency of interaction is so low.
Yeah.
The experimenting is not sensibly happening on a sensible timescale.
Yeah, you can't make a compound out of two atoms if they don't meet up, you know? So it's just, it's just slow. It happens. And you can get complex molecules, but it's slow. And molecular clouds don't live that long.
Oh,
Yeah, millions of years. They're a little transient. So
gotcha.
no, I'm sorry. That was an astronomical time scale there. That's fast.
Right.
So,
Okay. There you go.
But don't live, so what happens to them?
well, they could collapse to form stars, or they could dissipate or be disrupted. They're all very turbulent, so they could just fly to pieces.
Okay.
Yeah.
Okay. All right. This is Saja Minkinen. Saja Minkinen, who says, hello.
I'm
from
guessing
the-
it's not that.
Yeah, I mean, how about this?
I'm just guessing.
Saya Minkinen. Okay, how about that? Hello from the distant snowy lands of Finland. My name is Saya Minkinen, pronounced Saya. Oh, guess who got it right? Okay.
Oh,
For once. Had it wrong the first time until you said maybe not. The last name, sorry, I can't help you there, Chuck. Okay. You jackass. All right, here you go, Saya. Here's my question. If there are regions in the galaxy where stars are born and die very quickly, could these starbursts in some way be considered the vital functions of galaxies themselves? In other words, do they act as the breathing of the pulse of galaxies, shaping their life cycle and their evolution?
Boy, you sound like you've been working with Neil for a while. Yeah, that's a great question. And it's kind of the thing that got me into the Galaxy Cluster
pulse
Project.
of the galaxy.
Yeah. Because galaxies form from infalling gas and things like that, but then there's also this process of feedback because you get supernova explosions and things like that, or stellar winds, and when it's all happening in one burst like that, you can get these giant super bubbles or galactic scale winds that are coming out of galaxies and then reseeding their neighborhood and even turning off the star formation. So it's all regulated by these feedback mechanisms.
That's wild.
They also generate cosmic rays, which can carry away a bunch of the energy as well. It's another thing I've been looking at.
Very, very cool. Great question, Saya. Way to go. I'll forgive you for making fun of me. All right. This is Michael Kemp, who says, greeting Dr. Tyson, Lord Nice, Dr. Paglione, Paglione, sorry.
Rhymes with telephone, I tell my
There you go,
students.
Paglione. Michael Kemp here from soggy Oregon Coast Range in the southwest of Eugene. James Webb Space Telescope has imaged tons of supernova from the early universe. Are these early supernovae different from the ones occurring in our universe today? Thanks a lot. What would make them change?
Wow, it's a great question. It's actually a big problem. What we assume is that they're the same as supernova that we know and love, the ones that we're really familiar with that are nearby. And we're kind of hoping that they probably are the same so that we understand what they're like.
Right.
Now, what he's referring to, though, there's been dozens of new transients discovered by the James Webb Space Telescope. So things
Please
that
explain
just
transients.
yeah, things that just blinked on and then went away.
Oh, get out.
Yeah,
That don't repeat.
transient, like an explosion.
Wild. Okay. That's crazy though.
So we presumed they're supernova, but we're actually I think they're still studying what the heck they are.
Okay.
This is really new stuff. I mean, this guy's up on.
Yeah, he's up on his stuff. Way to go, Michael Kemp. Look at that. You impressed the doctor here. Okay. All right. This is Gavin Bamber, who says, hello from North Vancouver. Please visit us. Okay. Thanks for the invitation. I'll
Absolutely.
be expecting my plane ticket. Was our sun a star that was formed from the debris of a massive star? If so or not, how many dying stars does it take to form a new star. Interesting.
So yeah, we're definitely a second generation. The sun is definitely a second generation star, what we call a population 1 star, even though it's second generation. Pop 2 came first. I don't know, astronomers. But
Pop 2 came first, Pop 1 came second.
yeah.
Okay.
Deal with it.
That's weird.
There's Pop 3 now also, which were the
was
first
before
stars.
everything.
Yeah.
Okay.
Yeah.
That's ridiculous.
Anyway, well, the sun is definitely a Pop 1 star, so it has heavier elements in it, like magnesium and whatnot, And these things come from exploding stars and other evolved stellar things. So yeah, for sure, we're from the debris of a lot of different stars, though. So all that. When a star explodes or throws off its outer layers when it's a giant or things like that, that all goes back in the interstellar medium, eventually forms another giant molecular cloud, and then forms the next generation of stars.
Falls in and forms a star. That's pretty wild.
Next gen. Gen X.
I love it.
Let's start naming them.
We're a Gen X star.
Yeah, Population 1 and 2, that's not catchy.
Yeah, it really isn't.
Yeah.
Just start. All right. This is Alyssa Feldhaus. Alyssa Feldhaus, who says, Alyssa from Rocket City, Huntsville here. Dr. Paglione, can we trace the features in younger galaxies directly to these early starburst galaxies? And might they be considered progenitors of the galaxies we observe today? And why, pray tell, is my favorite candy named after them? Thanks for keeping me up. Okay.
Starburst.
Yeah.
Starburst. Right there. You have some on your desk over there.
Oh, very nice.
Look at that.
I mean, the answer to her question, in short, is yeah.
This is when you know you're in a real astrophysicist office. when you see some starbursts sitting around. Anyway, yeah, you want one? There you go.
I think that's just a cool name. I'm not in the marketing firm for these guys, but yeah.
Yeah, just went for it. Yeah.
In astronomy, Neil wrote about this a long time ago.
What's that?
We use simplistic naming.
Love it.
We're not super fancy with the names. If there's a burst of star formation in a galaxy, we call it a starburst galaxy.
Gotcha.
Get right to the point. But yeah, I mean, the earliest galaxies were forming a lot of stars. They were smaller, obviously, and really messed up. And yeah, we try to make those connections. But the star formation rate earlier in the universe was a lot higher than it is today. So things we're definitely interested in trying to tie all those together. Yeah.
Cool.
Time for one more question, Chuck.
All right, let's go to our buddy, Alejandro Reynoso.
He's from Hackensack, New Jersey.
Oh, okay.
He's
not the big king.
Alejandro Reynoso from Monterrey, Mexico. Hello. Or should I say, hola.
There's that on there.
No, he says this. My question is, how massive stars, how do they behave different from our sun? Is the only difference in how they die?
No, it's also in how they're born and how they live. So it's everything.
Oh, my God.
Yeah, massive stars do everything just fast.
So let's talk about how they're born, because that's pretty doggone interesting.
Well, it's the same way the sun or a low-mass star is born. It's a collapse of a molecular cloud.
Right.
But the massive star just does it faster because of the mass.
Because of all the mass.
Yeah,
and
gravity. So
And
it's
gravity.
just all happens faster.
All right. So now I'm this big, giant, fat superstar, and I'm just burning away, baby. What am I doing differently than the kind of star that we have? And then what am I doing differently than like a brown dwarf, like a little boring-ass brown dwarf star?
It's the burning away baby that you were talking about.
Oh,
it's
really?
the burning.
It's the burning.
It's all in the burning. So the sun at the core.
But just to be clear, we don't use the word burn the same way the chemist does.
Yeah.
Of course.
Yeah.
Of course you wouldn't.
The chemist burn is a chemical reaction,
Right.
usually involving oxygen,
Right.
where it's exothermic and releases. We say burn,
Right.
but we don't mean burn.
What you really mean is what? Well, we're reacting.
We mean thermonuclear fusion.
Fusion,
Of course.
yeah.
Yes.
But so it's loose tongue. It's just loose tongue. We all guilty of that.
Gotcha.
So I slipped
So,
that in there.
right.
Okay.
So here you are. You're doing your thermonuclear fusion.
Yes.
And
We're talking about hydrogen burning.
right.
But-
That's
Yeah.
hydrogen burning.
So that's what
And
the sun is
That's
doing.
the sun.
Yeah,
Right.
burning hydrogen and creating helium.
Right. So it's helium. So what's the big fat guy doing?
So they have enough mass to compress the core to higher temperatures so that they can burn helium into carbon.
Oh.
Or, even better, burn carbon into oxygen.
Oh.
Or, even better, the next one, and the next one, and the next one, until you get up to iron.
So they're just making all these elements.
Yeah.
As they burn?
Yep.
Whoa.
Nucleosynthesis.
Nucleosynthesis. So that is not just a part of the dying process before they explode.
That's the living process.
That's just the living process.
Yeah.
Interesting.
Yeah. And each one of those is a very energetic process, so they burn fast. Okay. And so even though, they have more mass, and so you would think, with more fuel in the tank, you'd last longer.
No,
they burn it up really, really fast.
Oh, really?
Way faster.
Yeah. They're super luminous. I mean, they could be thousands of times more luminous than the sun. Mm-hmm. And so they're shining, they're giving off energy that much faster.
Now, does the size compensate for the longevity, or do they just burn out quicker?
They burn out quicker.
Oh.
They might only last 10 million years.
Oh.
Yeah.
Instead of a trillion.
Right.
Yeah.
Yes.
Yeah. So this is why when star formation's happening, massive star formation, it's instantaneous. If you see there are no old massive stars.
Look at that.
There just aren't.
It's better to burn out than it is to fade away.
What's that from? That's
Highlander.
No.
Yes.
There's another one.
Really?
That's Highlander.
That has two catchphrases? It's not there can be only one?
That is the number one catchphrase.
Yeah.
But the anti-hero in the movie, that's his line. It's better to burn out than it is to fade away.
My favorite song that has that. It's better to burn out than to fade away. It's Neil Young.
Oh, Neil Young.
Hey.
My favorite Highlander line is actually, "It hurts, doesn't it?" He stabs him in the neck.
That's your favorite?
Yeah. Because it's kind of cruel because he knows he won't die. Just stabbed him in the neck.
Okay.
Hurts, doesn't it?
Wow. So big giant stars, they live fast and die young.
Absolutely.
Awesome.
Yeah.
Even though they have more fuel.
Even though they have more fuel.
They're like gas-guzzling land yachts of the 1960s and 70s.
I like to think of more.
They had bigger gas tanks, but they would not go as far
right.
as the smaller gas tank. They got better gas mileage.
That's right.
Same analysis.
Very cool.
Let me see if I can reflect on our conversation.
Yeah.
With a cosmic perspective.
Okay.
What has always fascinated me with science in general, but astrophysics in particular, is that there are things you know and love and see that you have telescopes and detectors, and you hypothesize what's there, and you get better data, and you figure it out. And then you realize you're still only limited by the power of your tools. And you wait until a bigger telescope comes along, a better telescope comes along, a more powerful particle accelerator comes along that could reach into zones of the universe that were previously unknown. And so for me, it's not just about how clever are you with what we already know. It's you got to bring in the engineers at some point to build the thing to be able to even see where you had never imagined was even possible. And that's where the significant growth in a field comes from. Not only from brilliant people thinking about stuff we already know about. It comes from brilliant technologies that could take us not only where we've never been, on occasion, where we've never even dreamt of. And that's a cosmic perspective. Tim, thanks for coming.
Hey, thank you.
Thanks for making the trip from upstairs.
Yeah.
Here at the Rose Center for Earth and Space, Hayden Planetarium, American Museum of Natural History. That's your visitor's office, right? Because you're based at York College.
That's right.
Yeah. So thanks for coming. We love
Absolutely.
your time here. Chuck, always good to see you, man.
Always a pleasure.
All right. This has been StarTalk, Cosmic Queries, the Extreme Energy Edition. Until next time, keep looking up.